Lesson 3.2 is exponential modeling. So we're going to specifically be looking at exponential growth and exponential decay. Equations you've probably dealt with. I don't know, it was brought up to me this morning that we did a little bit with exponential growth and decay in Algebra 2.
I remember that.
Okay. You may have very well seen this stuff in science.
Chem 2.
Very possible. Okay, so this will seem familiar from various aspects. Okay, so exponential population model. If a population P is changing at a constant percentage rate R each year, then P of T equals P naught times 1 plus R raised to the power of T. That is your general form of an exponential equation. And right here it's written with P's and T's. And actually, I think I'm actually going to also show it could also be written as f of x. Well, what do we... never mind. Not going to do that because I'm trying to think what I would use for the initial value. So, anyways, I'll demonstrate later. It can be written with x's and y's or x's and f of x's instead of p's and t's. But notice it says where I call that p naught is the initial population. It's P, maybe you call it P sub 0 or P0. I don't know what other teachers have necessarily called it, but that represents the population at time 0, and so it is the initial population. R, of course, is your percentage rate. Anytime you're in an equation, R is expressed as a decimal. And T, of course, is time in years. Okay, if your R value, your percentage rate, is greater than 0, then logic would say that it is an example of an exponential growth function, and 1 plus R is going to be your growth factor, which might be something you're asked for in homework. Okay. On the other hand, if R is less than 0, then we are talking exponential decay, and 1 plus R is the decay factor. And we're going to talk about that as we look at example 1 and example 1A and B, and as we talk about whether these are growth or decays. So, example 1, tell whether the population model is an exponential growth function or exponential decay function, and then find the constant percentage rate of growth or decay. As you look at A, P of T equals 782,248 times 1.0135 raised to the power of T. Thoughts?
It is.
It's an exponential growth function.
And why would we suggest growth?
Because it says so it has to be R. Hold on. R is bigger than 0. So when you add, like when you take 1 away from that, it's 0.135. So that's bigger than 0.
Okay. So if I rewrite this to demonstrate what she's talking about, 782,248, I'm following exactly.
Okay, I'm following.
And if you had kind of already had the same idea, you probably followed.
Yeah.
If you didn't already have that idea, you might be really confused. Yeah. So the idea is that 1.0135 can be rewritten as 1 plus 0.0135. And if we look at it in that form, it becomes fairly obvious. And there's two different ways I would say that we know this is a growth. And one way is because it was 1 plus a value, right? And we can also just look at the fact that because that number starts 1 point something. For those two reasons, I can look at this problem without really doing any work and okay, this is growth. This is an example of growth. If it's an example of growth, well, it is, not if. But we also were asked for our R value. That's a tongue twister. Thoughts on what our constant percentage rate of growth is? Where is R in this equation? You can also ask that. Start with that. What do you thought, Doug?
I would think 101.35%.
No. What is my R value according to the original function?
0.135.
R is just this piece here. And so if we look at just that piece there, the 0.0135, I think you had an extra 1 on the front, didn't you?
Yes, it's 100.
Yeah, okay. So what do we need to do to change 0.0135 to a percent? Multiply by 100, move the decimal to right, and so then this is 1.35%. Okay. So in other words, when we do the R value, we want to separate it from that 1. It's 1 plus the R value.
So then the growth factor would be 1.35?
The growth factor is actually just this 1.0135.
Okay, so then what is the 1.35? Is that just we have to put it in the...
That's 1.35 is our percentage rate.
Okay.
That is our constant percentage rate.
Okay.
Growth factor is slightly different. Okay. Okay. What about B?
Decay. Because, yeah.
Decay because, yeah.
Because it's less than
because
0.
it's less than 1.
Okay. The fact that that is 0 point something.
Yeah.
Okay. Less than 1. Because that piece right there is less than 1. That's going to tell me decay. Now, the whole part about R being less than 0. So this is basically saying our decay factor is less than 1. If I write this out, so 1,203,368, except, and then it's going to be 1 minus something raised to the t. And so there is the fact that it's going to be 1 minus something, there is the negative R value, the R less than 0 part. Does that solve the confusion there, I'm guessing?
Yes.
Okay. Now, I need a number to fill in that blank because we're going to need that number on our answer. This is 1 minus what?
I did 1 minus 0.9858 to figure out that.
So it's
0.0142.
Okay, does that make sense to everybody?
Yeah.
Because that was going to be my question is, okay, how do you get this 0.0142 number? And the easiest way is to take the 1 minus the given to find the other piece. Okay, so really the point of this is 0.9858. That's not really any of our answer, is it? Okay, so if you haven't already,
Okay.
we know this is decay.
And negative 1.42%.
I'm just going to state it as 1.42%. And the reason I'm saying that is because I've already stated it's decay. So since I've stated it is decay, that pretty much says, okay, that is a negative R value. Does that make sense?
Yeah.
So if you were already saying decay, would you say the negative?
Then, yeah, then you would think differently, yeah. Okay, are we good here? Those should be fairly basic.
Yeah.
Okay, next one should be fairly basic too, I think. Determine the exponential function with initial value 12 increasing at a rate of 8% per year. Okay, exponential function is of the form P of t equals P naught times 1 plus r to the value of t, yes? I know that because it said exponential function. Now, what was provided here?
You have your percent. Get rid of percent.
Okay? My percent is 8%. What's going to go in my equation, though?
0.08.
I say, I think you had it.
So 0.
Okay, I was going to say, I think you had too many zeros, although honestly I lost track. 0.08, right?
0.08.
Okay. Move that decimal 2 places. What else do we know?
Initial value of 12.
Okay. Initial value of 12. And so that's going to go in for P of 0. P naught, P of 0. What else do I know?
Increasing says a growth.
Okay. Because it says increasing, we're going to be adding. And we know it's a growth because it says increasing. You've got to have something indicating is this increasing or decreasing here. Okay, can we write our equation? P of t equals 12. Okay, and I wrote mine for the moment as 12 times 1 plus 0.08 raised to the t. But yes, what would you likely do? You would clean it up. P of t equals 12 times 1.08 raised to the power of t. I'm going to put an or on here because, and the reason I'm doing this problem did not specifically say anything about population, did it?
Yeah.
It just said exponential function. We use population because that's what was given up top, but you could also use f of x here, or y equals. And so if we do that, if we use f of x, it's f of x equals 12 times 1.08, but raised to the x power. I'll be honest, I don't have much of a care which way you do this. There's nothing specifying what variables we use. So I don't have much of a preference there, but I want you to be familiar both ways. Okay, if it says population, that's usually done in terms of t. If it doesn't, whatever makes you happy there. Okay? And you'll see it both ways in homework, depending on what you're talking about there. Okay, next section. Officially, it says solving exponential functions graphically. Now, what we're basically going to do is we're going to write an equation for this situation, and then we're going to solve it graphically. So, suppose a culture of 100 bacteria is put into a petri dish, and the culture doubles every hour. Predict when the number of bacteria will be 350,000. That's when the calculator comes into play, because that's a big number, isn't it? Now, let's see. I'm going to kind of take us step by step here. And we're going to kind of develop this equation. I want you to kind of think about it. So let's talk about what happens after 1 hour.
Maybe 200.
Okay, it doubles. It's 200, yes? So the idea that it's going to be 100, which was the initial, times 2. I'm going to leave a little bit of a blank there for a reason, which means it's 100 times 2 to the first, if you will, which is 200. Just go with some of that for the moment. It'll make sense when I do the next couple of rounds.
Yeah, that's where I'm
I promise, it'll make perfect sense after the next round or two. Because I'm going to do 2 more rounds of this thought process.
at. Okay.
Okay, so after 1 hour, you had your initial 100. It doubled, so you multiplied by 2. And you got 200, right?
Oh, so just raising the rate to a power.
So now, let's talk about what happens after 2 hours. Well, jump over here to the end if you want. After 2 hours, what's my...
200.
We're going to be at what?
200. Or we're going to be at 400, but it's 200 times 2.
Okay, I don't want to talk 200 times 2. We're going to be at a total of 400. Now, how do we get to that 400?
100 times 2 is
100
100 times 2.
times 2 for the first hour,
Yeah.
times 2 for the second hour, which is 100 times 2 to the second. Which I agree. Is it doing 200 times 2? It is, but that's not going to help me write the equation. So I'm not disagreeing with 200 times 2, but not what I want to write down. Is that better?
Because we're still trying to stick to the thing.
One more round. Where are we going to be at after 3 hours? So after 1 hour, we were at 200 bacteria. After 2 hours, we were at 400. Where are we going to be at after 3 hours? We're doubling, so we're going to be at 800 bacteria, yes? Now, if we break this down into pieces, where does that 800 come from? The initial 100 times 2 for the first hour, times 2 for the second hour, times 2 for the third hour, which is 100 times 2 to the third. Now, the reason I'm having us do this is because we're going to use this thought to write our equation. Yep. Actually, I was actually using t, but yes. So the idea is if I write my equation, what was my initial? It was 100, and what were we doing every time? 2 to the x, so however many hours. Now, that wasn't part of our original form, just having a 2 there, is it? But think with me. If something doubles, how much is that? What is its growth rate? What is it? How much is it growing by? If something's doubling,
Times 2 in size.
it's times 2 in size, or it's growing 100%,
Yeah.
right? So if you think, so in other words, we could think of this as, whoops, 1 plus 1 raised to the power of x, if you will, because it's the original 100% plus an additional 100%, which is 200%. If something's doubling, it's growing to 200% its original size. Now, okay, here's the equation I wanted you to come up with, right? And the shortcut of it is every time you have to write a doubling equation, what's that base going to be? It's going to be a 2 every time you have to write it. So that's an easy way to remember it. Now, all that work just to write an equation. What was this question actually asking? When will we have 350,000? Well, I can tell you when we have 800, but we need to know 350,000. Now, if we just wrote an equation,
But you can't put it in.
okay, so what we're going to do is we're going to use the graph. Okay, because basically, yes, we want to know when does 100 times 2 to the x equal 350,000, right?
Mm-hmm.
So if we want to know when does 100 times 2 to the x equal 350,000, well, basically, we're going to graph both of these. We're going to graph y equals 100 times 2 to the x, and we're going to graph 350,000. And our goal is going to be to try and find out when they cross, they intersect. Okay, grab those calculators if you haven't already. Oh no, my TV turned off.
Zeros, 4, 6.
350,000, so 4 zeros.
Oh.
So work on graphing those two. Seeing if you can finagle it.
So, do you suggest the box or what?
Okay, well, let me get mine. 100 times 2 to the x and 350,000. I've got both equations typed in. Now, I don't know what I last graphed, so I'm going to do a zoom 6 just to start here because I need something. Now, notice you can see the one equation, right? Y equals 350,000. Can I see that? No, because y equals 350,000 is going to be a straight line, horizontal line at 350,000. My graph's nowhere near there, is it? So what I would consider doing is, I don't even know that I would use my zoom options here. I would consider going up to my window, and instead of my y min and y max being -10 and +10, put them something around 350,000.
Yeah.
So below 350,000, I could do 349,900. And then above it, I could do 350,100. I don't know, I just picked random numbers there. But something below and above 350,000. Now, when I graph this, now I have the opposite issue. I have my horizontal line, which is good, but my other one didn't come into play. Now, in all honesty, do I need negative x values? This isn't going to happen in negative time, is it? So, I would, one more time, change my window. First of all, I would make my x min 0. I don't need to see the negatives. And x max, I know where the answer lies, so I know if I double this and go 20 that we're going to be able to see the answer. But I would just kind of do some guesstimating until you see both graphs on your calculator. So if I make it 0 to 20, it's not actually a vertical line, that's just kind of what it looks like right now. But do I have an intersection point?
Yeah.
Okay. I don't know if we've ever used this function. Have we ever used the intersect function?
No.
Okay. So you know where you can find zeros and mins and maxes?
Yes.
Guess what there also is?
Intersect.
Intersect. So if I go into second calc, and I go down to number 5, intersect, the first question it's asking is, what do you want your first curve to be? For me, it has the 100 times 2 to the x. Just as long as it has one of your curves highlighted. And if you only have 2 curves in, you're not even going to have to change anything. So I'm going to hit enter. Then it says, what does it want my second curve to be? Well, 350,000. That's what it says up there, yes? So now I have my 2 curves. Guess. What's a guess say to do?
Oh my god.
Move my cursor to the area of where I want to see. And now it's telling me the intersection point is 11.773139 and 350,000. Okay, so the idea here was,
Please pardon the interruption. Students, if you left your Invisalign retainers in the cafeteria during lunch today, we have them in the high school office. Again, if you left your Invisalign in the cafeteria during lunch, we have them in the high school office. Thank you.
okay, so the idea here is we want to look and see, we used our second calc menu or second trace, and we used the intersect option. Okay, so I graphed the curve, I graphed the line, and I'm looking for the intersect option. And my intersection was at 11.773139 and 350,000. So what does that mean my answer is? When will the number of bacteria be 350,000?
12.
I even have 11.77 hours. Okay, so I'm going to say intersects at t is approximately 11.77 hours. Because if you think about it, Does that have to be exactly 11 hours or exactly 12 hours?
No.
No, this is bacteria doubling, right? That can happen in seconds. That can happen, you know. And so that 11.77 hours is a more specific answer. Okay? Okay, one more. Example 4. Now we get to talk about half-life.
Oh, I remember this.
Suppose the half-life of a certain radioactive substance is 20 days, and there are 4 grams present initially. Find the time when there will be 1 gram of the substance remaining. Now, this one will actually work out a little bit easier for us because we don't have such a big number as 350,000. If I try and get you guys to think like we did the last time. The last time it was after 1 hour, 2 hours, 3 hours. This time, what's our first interval we need to think about? And the reason I did 1 hour, 2 hour, 3 hours is because my culture was doubling every hour, yes? What's my time span here we need to think about? Every
20 days.
20 days. So basically, I'm going to say after the first 20 days. Okay, after 20 days. Where are we going to be at?
2 grams.
2 grams because we're going to do the initial 4 times a half, which is 4 times 1/2 to the first, if you will, which is 2 grams.
Are we leaving a gap?
I did leave a little gap. I only really can do 1 more cycle. So that was after 20 days. What's the next increment we want to say?
40 days.
After 20 more days, which is going to be after 40 days. Well, first of all, half of 2 is 1, so we're going to be down at 1, aren't we? But how do we get that? The initial 4 times a half times a half again. Or in other words, 4 times 1/2 to the second. Well, we actually just answered our question. Did you realize that? Find the time when there will be 1 gram of the substance remaining.
40 days. After.
Okay, so the answer to the problem is after 40 days. Now, I can't remember exactly what's in homework, but I do want to talk real quick. No, I kind of put that in the wrong answer area. Oh well. What would have been my equation here?
P of T equals 20 times 1/2 X, or 1/2 T.
Not exactly.
4 1/2 T.
Okay, so 4. Oh, this is where, okay. 4 1/2. Now, here's the deal. It's not T, though.
Is it X or P?
Because, okay, so look at this with me. I forgot about this detail. I should have led a little bit differently. We had a 1 and a 2 there, yes? But what were we, this 1 was after 20 days. This 2 was after 40 days. So we kind of need a way to think that through. And the idea is after 20, this 1 here was because it was after 20 days out of a 20-day half-life. This one was because it was 40 days in a 20-day half-life. Are you seeing where I'm going with this? So the idea is this exponent then
Is 20?
is not 20,
It's T over 20.
x or t over 20. Because I wrote P of T, I'm going to say T over 20. Okay. Now, the last time it didn't really matter because it's just once every 1 hour. So I didn't have an issue with the timing there. This time I had an issue with the timing because it wasn't every 1 day, it was every 20 days. So just beware because you do have to write a couple of equations, I think. I want you to realize why that is. Now, the doubling had a 2 here, yes? What's half-life have? A 1/2. Now, why is it 1/2? If it's half of something, you're taking away what?
Divide by 2.
You're taking it divided by 2, or you're taking away half of something, or 50% of something, yes? So if you take away 50% of something, that's why it's so your R value is 50.
Yeah.
Or 0.5 because it's 50%.
So the 2 and the 1.
So the 2 and the 1, I mean, it's easy to say, oh, doubling. I know it's going to be 2.
Yeah.
Half-life, it's going to be a half. But there's a reason why it's the 2 and the 1/2. Okay. What is it on?
Page 264.
Page 264. 1 through 18.
I hate that we don't have any evens.
Yeah,
That's
why
not
would
just
they in
evens.
It's the odds.
So that we only have 9 questions.
Yeah, we always
Oh.
do the evens.
Okay.
Just the back of the book.